Our Sun is a cosmic speck of dust next to the universe's true giants. We are embarking on a journey to explore the most massive stars, and I promise you 30 facts that will completely redefine your understanding of these celestial titans. You will discover how their violent lives forge the very elements that make up our world, and how their spectacular deaths seed the cosmos with new worlds. What mysterious force prevents these stars from growing infinitely larger, and what catastrophic fate awaits them when their own power turns against them? What one quality do you think defines a true giant of the cosmos? Mass is the single most important quality for any star. It dictates everything from the searing intensity of its light to the spectacular way it will eventually die. When we talk about a truly massive star, we are not discussing something a little bigger than our own sun. We are talking about celestial behemoths that begin their lives with at least 8 times the sun's mass, and they only get more staggering from there. Think of the difference between a small, efficient car and a thundering freight train. Both are vehicles, but the scale of their engines, the power they generate, and the impact they have on their surroundings are worlds apart. Our sun is that reliable car, burning its fuel steadily for billions of years. A massive star is that freight train, barreling down the cosmic tracks at unimaginable speeds, pouring out a torrent of energy and destined for a far more dramatic final stop. This immense mass creates a crushing gravity in its core, forcing the star to burn its nuclear fuel at a furious, profligate rate. It lives fast, shines brilliantly, and dies young, and in that short, violent life, it forever changes the universe around it. Our sun, for all its life-giving brilliance, is a cosmic lightweight. To put its scale into perspective, our star is 333,000 times more massive than our entire planet Earth. Yet in the grand stellar census, it is classified as a G-type main sequence star, a perfectly ordinary and common kind of star. The true giants we are exploring dwarf our sun to an almost incomprehensible degree. We are discussing stars that can be over 100 times more massive than the sun. Imagine taking our entire solar system's central star, a celestial body of almost unimaginable power from our human perspective, and then piling 100 of them together. That is the scale of a single, truly massive star. This staggering comparison is not meant to diminish our sun, but to establish the mind-bending scale of the cosmos. Our local star is a reliable, steady candle, but the universe also builds roaring, short-lived bonfires that rewrite the rules of physics itself. This tremendous mass cannot grow indefinitely. There is a cosmic speed limit, a theoretical ceiling for how large a single star can become. For decades, astrophysicists have pointed to the Eddington limit, a boundary that caps stellar mass at around 150 to 200 times that of our sun. The reason for this limit is a constant, ferocious tug of war deep within the star. On one side, you have the crushing force of gravity, pulling everything inward, desperate to feed the star more gas and dust. On the other side, you have the unimaginable radiation pressure generated by the star's own nuclear fusion. Think of a star as a cosmic construction site. Gravity is the crew, constantly hauling new building materials onto the site. But the star's core is also a non-stop demolition derby, blasting out so much light energy that it acts like a powerful wind, blowing all the new construction materials away. At the Eddington limit, these two forces reach a stalemate. The outward push of radiation becomes so overwhelmingly strong that it perfectly counteracts the inward pull of gravity. The star simply cannot hold onto any more material. It has reached its maximum possible size, yet the cosmos loves a good mystery. Recent observations have spotted a handful of stellar monsters like R13601 in the Tarantula Nebula that appear to tip the scales far beyond this accepted limit. This has sparked intense debate among astronomers. Are we seeing colossal binary stars masquerading as single entities, or are our fundamental theories about star formation in need of a rewrite? The very existence of these supermassive outliers challenges our understanding of how the universe builds its largest stars. This theoretical limit is embodied by a single, almost mythical star. In the heart of the Tarantula Nebula, a vast and violent stellar nursery in a neighboring galaxy, lies the reigning heavyweight champion of the known universe, a star known as R13601. At its birth, this colossal object is estimated to have possessed a mass between 196 and 315 times that of our Sun. To grasp that number, picture a single newborn star that outweighed our entire solar system's central furnace by a factor of over 200. It is a scale that pushes the very boundaries of what we believe is physically possible for a star. Today, it has shed a significant portion of that mass, but it remains an unparalleled monster. Its energy output is even more difficult to comprehend. R13601 does not merely shine, it rages with the ferocity of nearly 9 million suns combined. If you were to place this star at the center of our solar system, its searing light would not only vaporize Earth instantly, but its outer atmosphere would extend beyond the orbit of Jupiter, swallowing the inner planets whole. Pinpointing the exact properties of such a distant titan is one of astronomy's greatest challenges. Scientists must peer across 163,000 light-years of space, analyzing the subtle signatures in its light to weigh and measure it. The very fact that it exists at all forces us to question our models, suggesting that the universe might have even more extreme methods for building its giants than we have ever dreamed. But how can we possibly know the mass of a star located millions of light-years away? We cannot exactly place a celestial giant on a cosmic scale. Astronomers have to be far more clever, using indirect methods to weigh these distant behemoths. The most reliable technique involves studying stars that are not alone. When two stars orbit each other, forming a binary system, they are bound by the unbreakable chain of gravity. By carefully observing their dance, we can apply the same laws of motion that govern our own solar system. We measure the time it takes for them to complete an orbit and the distance between them. These two simple pieces of information, plugged into the equations first described by Johannes Kepler centuries ago, allow us to calculate their combined mass with stunning accuracy. It is like watching two dancers spinning around a central point. By timing their spins and measuring how far apart they are, you can deduce how heavy they both are, even from a tremendous distance. For stars that travel solo, we use a different cosmic tool, the Hertzsprung-Russell diagram. This powerful chart plots a star's color, which tells us its surface temperature, against its true brightness or luminosity. Stars are not scattered randomly across this diagram. They fall into specific, predictable regions. A star's mass is the primary engine that dictates where it will appear on this map. A massive, hot, blue star will blaze from the top left of the diagram, while a smaller, cooler, red star will glow modestly from the bottom right. Once we know a star's temperature and its intrinsic luminosity, we can place it on this chart and simply read its mass from its position. It is a cosmic cheat sheet, a direct link between the light we can observe and the hidden engine that produces it. These methods transform abstract points of light into known quantities, giving weight and substance to the giants that rule the cosmos. This staggering mass translates into a light output that defies all human intuition. The relationship between how heavy a star is and how brightly it shines is not a gentle, proportional one. Instead, it is a runaway explosion of energy governed by a simple yet brutal mathematical law. We call this the mass-luminosity relation. For main sequence stars like our Sun, the luminosity is proportional to the mass raised to the power of 3.5. That exponent is the key to everything. It means that if you double a star's mass, its brightness does not merely double, it increases by a factor of just over 11. But the real magic, or perhaps the real terror, happens at the extreme end of the scale. Consider a star that is 10 times more massive than our Sun. You might logically assume it would be 10 times brighter. The reality is far more spectacular. 10 raised to the power of 3.5 is approximately 3,162. That single star is not just a little brighter, it is over 3,000 times more luminous than our Sun. It is the difference between a single candle and a colossal bonfire that can be seen from across the galaxy. This incredible energy comes from a frantic, desperate race against gravity. The immense weight of the star's outer layers crushes the core, forcing the nuclear furnaces there to burn their hydrogen fuel at a feverish, unsustainable pace. A star like this is not merely shining, it is hemorrhaging energy into the void, living a life of glorious, extravagant excess. It is this profligate spending of its fuel reserves that seals its fate, dooming it to a short, violent life. How can anything sustain such a furious output for long? This extravagant energy output comes at a devastating personal cost. The very power that makes these stars so brilliant also ensures their lives are tragically short. Our own Sun, a model of cosmic stability, is expected to shine steadily for about 10 billion years, a span so vast it cradles the entire history of life on our planet. But a star just 20 times more massive than the Sun lives a life of frantic haste. It will exhaust its entire supply of hydrogen fuel in roughly 10 million years. To grasp that disparity, imagine comparing a single human lifetime to a single fleeting day. That is the tragic irony of stellar mass. The most spectacular giants are cosmic mayflies, burning through their entire existence in what amounts to a mere blink in the universe's long memory. The reason for this fleeting existence lies deep within the star's core. That crushing weight of overlying material creates a pressure cooker of unimaginable intensity, driving the core's temperature to soaring heights. In this superheated environment, nuclear fusion does not proceed at a gentle, steady pace. It becomes a frantic, runaway chain reaction, consuming hydrogen fuel at a prodigious, almost wasteful rate. A massive star is not a careful saver, it is a billionaire on an endless spending spree, and its vast fortune of hydrogen is depleted in a cosmic instant. This rapid consumption forces the star to evolve at a breakneck speed, rushing through its life stages with a dramatic urgency that smaller stars will never experience. Its glorious light is the glow of its own rapid self-immolation. This frantic, brilliant life begins with the simplest of ingredients, the same primordial stuff that birthed every star in the sky. A newborn giant is almost entirely hydrogen and helium, the two lightest and most abundant elements forged in the Big Bang. Its immense structure coalesces from a collapsing cloud of gas and dust, a cosmic womb that provides the raw fuel for its future fires. Yet not all stellar nurseries are created equal. The environments that give rise to these true titans are far more extreme than the quiet nebula that spawned our own Sun. They are dense, chaotic, and often already polluted with the ashes of long-dead stars. Within these violent stellar factories, the gas clouds can be seeded with traces of heavier elements like carbon, oxygen, and iron, elements that were forged in the cataclysmic explosions of previous generations of massive stars. This subtle enrichment from the very beginning can influence the star's development, altering its opacity and how its intense radiation interacts with its own outer layers. While a star's destiny is overwhelmingly dictated by its mass, this initial chemical fingerprint is a whisper from a past cosmic tragedy, a legacy of violence woven into the fabric of the newborn giant. This initial chemical makeup, this fingerprint from its birth cloud, is what astronomers call metallicity. It is a slightly misleading term because in astronomy, a star's metallicity refers to the proportion of its mass that is made up of any element heavier than helium. This includes everything from carbon and oxygen all the way to iron and gold. It is not just about metals in the everyday sense, but about all the complex elements that were forged in stellar furnaces long before this new star was born. This single property, metallicity, acts as a powerful throttle on a star's evolution. A star born with lower metallicity has a clearer, more transparent atmosphere. This allows the intense radiation blasting from its core to escape more easily. With less radiation pressure pushing outward, gravity can pull more material inward, potentially allowing the star to grow to a more monstrous size before it reaches that Eddington limit. This simple principle leads us to one of the most profound and elusive ideas in all of cosmology. In the very early universe, just after the Big Bang, there were no heavy elements at all. The cosmos was a vast, pristine sea of hydrogen and helium. The first stars to ignite in this primordial darkness must have formed in an environment of virtually zero metallicity. We call these hypothetical first giants population 3 stars. Unencumbered by the elements that make modern stars more opaque, these primordial behemoths could have grown to almost mythical proportions. Theories suggest they may have been colossal spheres of pure hydrogen and helium, with masses ranging from 100 to over 1,000 times that of our Sun. They would have been titans of unimaginable brightness, living violently and dying young. Their spectacular deaths as supernova, or perhaps even as universe-shaking hypernova, would have been the crucibles that forged the very first heavy elements. They polluted the pristine cosmic gas with the ashes of their own destruction, seeding the clouds that would eventually form the next generation of stars, the ones with planets and ultimately life. We have never directly observed a population 3 star. They are ghosts from the cosmic dawn, but their legacy is written in the chemical composition of every star that came after, including our own Sun. The iron in your blood and the calcium in your bones were first forged in the hearts of those long-vanished primordial giants. That frantic outpouring of energy does not just radiate away as light. It physically tears material from the star's own surface, blasting it out into the void in a continuous, ferocious gale. These are stellar winds, and for a massive star, they are a hurricane of cosmic proportions. The force behind this relentless erosion is the same radiation pressure that defines the star's maximum size. The photons of light generated in the core carry momentum, and when they slam into atoms in the star's outer atmosphere, they push them outward with incredible force. The result is a wind that makes our Sun's gentle solar breeze seem like a whisper. A typical massive star can generate a stellar wind millions of times more powerful, streaming away from its surface at speeds of several million miles per hour. This is not a gentle loss, it is a constant, violent stripping away of the star's own substance. Over its short lifetime, a true giant can lose a significant fraction of its total mass through this process alone, blowing a vast, tenuous bubble in the surrounding interstellar medium. But sometimes this steady loss erupts into something far more dramatic and catastrophic. Look no further than the star Eta Carinii, a notorious and unstable behemoth in our own galaxy. In the 1840s, it underwent a colossal eruption, an event so violent it briefly became the second brightest star in the entire night sky. In that single outburst, it ejected at least 10 times the mass of our entire Sun. This expelled material formed 2 vast, expanding lobes of gas and dust, a structure we now call the homunculus nebula. This beautiful bipolar cloud, visible through powerful telescopes, is the ghostly echo of a star's violent struggle against its own immense power. It is a monument to the sheer force of these stellar winds when they spiral out of control, a permanent scar in space from a star literally tearing itself apart. These ferocious stellar winds can eventually strip a star down to its very bones. For the most massive stars, this process culminates in one of the most extreme and short-lived phases known to astronomy, the Wolf-Rayet stage. This is the star's final, defiant act before its inevitable destruction. Imagine a star that has been completely skinned alive by its own radiation. The relentless hurricane of its stellar winds has blown away its entire outer envelope of hydrogen, the very fuel that powered its main life. What remains is a blistering hot core, now fully exposed to the vacuum of space. This core is no longer fusing hydrogen. It is burning helium into even heavier elements like carbon and oxygen. The surface temperature of a Wolf-Rayet star soars to staggering levels, often exceeding 100,000 degrees Celsius. It glows with an intense, searing blue-white light that is almost too violent to comprehend. Astronomers first identified these stars not by their appearance, but by the bizarre fingerprint of their light. When they spread a Wolf ray, its light, into a spectrum, they do not see the familiar dark absorption lines of a normal star. Instead, they see brilliant, broad emission lines, massive smears of light from elements like helium, carbon, and nitrogen. These lines are so broad because they are generated in the star's own supersonic wind, a chaotic maelstrom of gas being blasted away at millions of miles per hour. The sheer violence of this outflow smears the light signature, creating a spectrum that screams of a star in its death throes. This is a star actively disassembling itself, broadcasting its own dissolution across the galaxy. This spectacular phase is brutally brief, lasting perhaps only a few 100,000 years. In cosmic terms, that is less than the blink of an eye. But in that fleeting moment, a Wolf-Rayet star serves as a crucial cosmic forge. Its powerful winds blast vast quantities of newly processed elements directly into the surrounding space. Carbon, oxygen, and nitrogen are flung out into the interstellar medium, seeding future generations of stars and planets with the building blocks of complexity. A Wolf-Rayet star is quite literally scattering its own guts across the galaxy. This act of self-destruction is the direct prelude to an even greater cataclysm. Having shed its outer layers, the star's core is now primed for collapse. It is a ticking time bomb, destined to end its life in one of the universe's most energetic events, a supernova explosion that will forge even heavier elements and scatter them far and wide. The star's final, furious winds are just the opening act for the main event. This layered structure is a direct result of the star's desperate struggle against gravity's relentless pull. As each type of nuclear fuel is exhausted at the very center, the core contracts under its own immense weight. This contraction generates even more crushing pressure and heat until the temperature soars to a new, even more extreme threshold. At that point, a new type of fusion ignites in a shell surrounding the now inert core, while the next stage of nuclear burning begins at the very center. This process repeats itself, creating a nested series of fiery shells, each fusing a heavier element than the last. It is a frantic, multi-layered race against time. In the outermost shell, hydrogen is still fusing into helium. Deeper inside, a shell of helium fuses into carbon. Further in, carbon atoms are crushed together to form neon, then oxygen, and then silicon. Each layer burns hotter and faster than the one before it. The hydrogen shell might burn for millions of years, but the silicon-burning core at the very heart of this cosmic onion will complete its work in less than a single day. This entire intricate structure is built around a final, inert core of iron and nickel. This iron heart is the end of the line for fusion. Fusing iron does not release energy, it consumes it. For a brief, terrifying moment, the star's ultimate energy source simply vanishes. The furious radiation pressure that has supported this colossal structure against its own weight for millions of years suddenly winks out. The entire star, a titanic object layered like a finely crafted artifact, is left standing on a trapdoor. The countdown to total collapse has begun, and the clock is ticking down from 1 second to 0. Iron is the ultimate cosmic poison. Its formation deep within a star's heart signals an immediate and irreversible death sentence. For millions of years, the star has been a delicate balancing act, with the outward push of radiation from fusion perfectly countering the inward crush of gravity. But fusing iron into heavier elements is fundamentally different from all the fusion stages that came before. Instead of releasing a tremendous burst of energy to prop up the star, the process of creating elements heavier than iron actually consumes energy. It is a nuclear reaction that acts like a power drain, not a generator. In that final, searingly hot core, the star's primary energy source simply vanishes. The radiation pressure that has supported this colossal structure against its own immense weight for its entire life instantly disappears. With nothing left to hold it up, the star's own gravity, the very force that gave it birth, becomes its executioner. The balance is shattered. In less than 1 second, the iron core, which can be as massive as 1.5 times our entire sun, experiences a catastrophic, uncontrolled collapse. It falls inward at velocities approaching 1/4 of the speed of light. This is the iron catastrophe, the single most pivotal moment in the life of a giant star. It is the trigger that unleashes one of the most violent events the universe can produce, a supernova explosion that will, in its final act of destruction, forge all the elements that make our world possible. The collapse of that iron core happens in the blink of an eye. As the core compresses to an almost unimaginable density, protons and electrons are forced together, merging to form neutrons and releasing a flood of ghostly particles called neutrinos. In that final, desperate moment, the core becomes an incredibly dense sphere of pure neutrons, a city-sized object containing more mass than our entire sun. This new neutron core is so rigid it cannot be compressed further. The inward-falling material from the rest of the star smashes into this newly formed, impenetrable wall and rebounds. This rebound sends a cataclysmic shockwave racing back outward at hypersonic speeds, a final, violent rejection of gravity's pull. This is the moment of the core collapse supernova. The shockwave rips through the star's carefully layered structure, blasting the entire outer envelope into the void of space. The star is torn apart in a single titanic explosion. For a few glorious weeks, the light from this single dying star can outshine the combined output of every other star in its host galaxy. It is a brief, spectacular funeral pyre visible across the cosmos. But this explosion is more than just a light show. It is the universe's ultimate forge. In the heart of that unimaginable maelstrom of energy and neutrons, in a process known as rapid neutron capture, elements heavier than iron are born. The gold in a wedding ring, the silver in a piece of jewelry, the uranium that fuels nuclear reactors, all of these were created in the frantic final seconds of a massive star's life. The supernova scatters these newly minted elements far and wide, mixing them with the surrounding interstellar gas. This enriched material will eventually collapse to form new stars, new planets, and one day, new life. We are literally made from the ashes of these long-dead giants. That final, spectacular explosion is not the end of the story. The death of a giant star leaves behind a ghost, a rapidly expanding cloud of incandescent gas and dust known as a supernova remnant. For thousands of years, this beautiful, chaotic structure will continue to glow, a fading echo of the star's final cataclysm. Perhaps the most famous of these cosmic ghosts is the Crab Nebula, the tangled wreckage of a star that exploded in the year 1054, an event so bright it was seen and recorded by astronomers across the ancient world. Today, through our telescopes, we see a complex web of glowing filaments, a tapestry woven from the star's own expelled guts, still rushing outward at millions of miles per hour. But this remnant is far more than just a memorial. It is a cosmic engine of creation and destruction. The same shockwave that tore the star apart continues to plow through the surrounding interstellar space, acting like a cosmic snowplow. It slams into nearby clouds of cold, quiet gas and dust, compressing them with unimaginable force. This violent trigger can be the very push needed to overcome a cloud's internal resistance, causing it to collapse under its own gravity and ignite new stars. The death of one giant star can thus give birth to an entire new generation of stars and potentially their planets. Furthermore, within the remnant's turbulent heart, magnetic fields trap and accelerate subatomic particles to nearly the speed of light, creating intense sources of X-rays and generating the mysterious high-energy particles we call cosmic rays. For millennia, a supernova remnant remains a vibrant, dynamic hub of activity, a crucial player in the galactic ecosystem that enriches, energizes, and reshapes the very fabric of its corner of the universe. Yet that collapsed core has its own, equally spectacular destiny. If the remaining stellar corpse weighs between 1.4 and 3 times the mass of our Sun, it does not simply fade away. It is reborn as one of the most bizarre objects in the universe, a neutron star. This is the final, defiant state of matter where the rules of everyday physics are completely rewritten. In that final second of collapse, the core's protons and electrons are crushed together with such inconceivable force that they merge, transforming into a solid, city-sized sphere of almost pure neutrons. The density of this object is beyond human comprehension. Picture a single sugar cube from your kitchen. Now imagine that tiny cube of material weighing as much as every single person on Earth combined, over 1 billion tons compressed into a space the size of your fingertip. A neutron star is matter pushed to its absolute breaking point, where atoms themselves have been obliterated. This incredible density is matched by its ferocious spin. Just as an ice skater pulls their arms in to spin faster, the conservation of the original star's angular momentum causes the newly formed neutron star to rotate at dizzying speeds. A star that once rotated sedately once every few weeks can now be spinning hundreds of times every single second. Along with this rapid spin comes a magnetic field of almost unimaginable power. These fields are trillions of times stronger than Earth's protective magnetic shield, so intense that they can distort the very structure of atoms in the space around the star. This cosmic powerhouse, born from utter collapse, becomes a beacon of extreme physics, a laboratory for conditions we could never hope to recreate on our own world. But what happens when even the formation of a neutron star is not enough to halt the collapse? For the cause of the very most massive stars, gravity wins its final, absolute victory. When the remaining stellar corpse weighs more than about 3 times the mass of our Sun, no known force in the universe can possibly support it against its own weight. Not the fierce pressure of a degenerate neutron core, not the energy of fusion, nothing. The collapse that began with the iron catastrophe simply continues, accelerating into an irreversible descent. The core crushes itself down to a single point of infinite density, a singularity. The star's own mass vanishes from the visible universe, leaving behind only its immense gravitational pull. This is the birth of a stellar mass black hole. The defining feature of this new object is not the singularity at its center, but the boundary that surrounds it, the event horizon. This is the point of no return, a spherical surface where the escape velocity equals the speed of light. Imagine a cosmic waterfall. The event horizon is the lip of the waterfall. Space itself is flowing inward faster than light can swim against the current. Once anything, even a single photon of light, crosses that invisible threshold, it can never climb back out. It is lost to our universe forever. This is the ultimate legacy for the most colossal stars. Their lives of extravagant power and furious fusion culminate in the creation of the most enigmatic objects in existence, regions of space where gravity is so absolute that it bends the very rules of reality. For stars that push mass to its ultimate extremes, even a core collapse supernova is not the final word. There exists a theoretical class of stellar detonation so utterly complete, so profoundly violent that it erases the star from existence entirely. This is the pair instability supernova, a fate reserved for stars born with a mass between 130 and 250 times that of our Sun. Within the cores of these almost mythical giants, temperatures soar to levels that defy comprehension. The radiation trapped inside is not mere visible light, but an intense bath of gamma rays, the most energetic form of light in the universe. Under these staggering conditions, something bizarre and catastrophic occurs. The gamma-ray photons themselves, the very particles of light that provide the outward pressure holding the star up, spontaneously transform. A single gamma-ray photon carrying immense energy can suddenly convert its pure energy into matter, creating a pair of particles, an electron and its antimatter counterpart, a positron. This process, matter-antimatter pair production, is like robbing a building of its structural supports to create new, useless bricks. The outward radiation pressure that was fighting gravity plummets dramatically. With its primary support system failing, the core experiences a sudden, catastrophic collapse. This is not the gentle fall that leads to a neutron star. This is a runaway implosion that heats the core to even more insane temperatures until it reaches a critical flashpoint. At that moment, the entire star, from its center to its outer layers, undergoes a runaway thermonuclear fusion reaction. The entire structure is fused into heavier elements in an instant, and the resulting energy release is so titanic that it does not leave a remnant. There is no neutron star, no black hole. The entire star is utterly and completely vaporized, blasted into a cloud of incandescent gas and freshly forged elements. It is the most absolute form of stellar suicide possible. A final, brilliant flash that leaves nothing but an expanding cloud of dust and an echo of pure, unadulterated power. These stellar corpses can become the universe's most precise timekeepers. When a neutron star's intense magnetic field and its rapid rotation align, it transforms into a celestial beacon known as a pulsar. The star's powerful magnetic field focuses its radiation into two narrow, intense beams, shooting out from its magnetic poles. Crucially, these magnetic poles are often misaligned with the star's rotational axis. This means that as the neutron star spins, these beams sweep through space like the blazing rays of a cosmic lighthouse. If our solar system happens to lie in the path of one of those sweeping beams, we detect a brief, incredibly regular pulse of radiation with each rotation. The clockwork precision of these pulses is almost unnerving. Some pulsars rotate hundreds of times every single second, and their pulses arrive with a consistency that rivals and often surpasses the most accurate atomic clocks we can build on Earth. This phenomenal regularity makes pulsars far more than just cosmic curiosities. They are powerful tools for testing the very fabric of reality. By carefully monitoring the timing of pulses from a pulsar in a binary system, astronomers can study how its orbit decays over time, providing some of the strongest indirect evidence for the existence of gravitational waves, exactly as predicted by Einstein's theory of general relativity. This precise timing also opens up a visionary possibility for the future of space exploration. Just as ancient sailors used lighthouses to navigate treacherous coastlines, future interstellar travelers could use the predictable pulses from a network of pulsars as a galactic positioning system. By comparing the arrival times of pulses from several known pulsars, a spacecraft anywhere in the galaxy could triangulate its position with astonishing accuracy, navigating the starry ocean without ever needing to look back at Earth. But even a typical neutron star is not the final word in cosmic extremes. Some of these stellar corpses are born under conditions that twist their already immense magnetic fields to almost incomprehensible levels. These are the magnetars, the true magnetic monsters of the universe. A magnetar possesses a magnetic field that is not merely strong, but 1,000 trillion times more powerful than the magnetic field that protects our planet. To grasp that number, imagine a single magnet so potent that it could erase every credit card on Earth from a distance halfway to the moon. This ferocious magnetism is locked into the neutron star's solid, ultra-dense crust, placing the entire structure under unimaginable strain. The crust of a magnetar is not a placid surface. It is a rigid lattice of iron nuclei, strained to its absolute breaking point by the magnetic forces twisting within. Occasionally, this strain becomes too much to bear, the crust cracks. This event is a starquake, a seismic shudder on a stellar scale, but this is no ordinary tremor. The energy released in a single starquake is more than the Sun will emit in 150,000 years, all unleashed in a fraction of a second. This cataclysm does not produce sound or shaking in the traditional sense. Instead, it violently whips the magnetic field lines, which in turn accelerates particles to near light speeds, resulting in a colossal flash of gamma rays and X-rays. These bursts are so luminous they can temporarily outshine every other source of high-energy light in the entire galaxy. The power of a magnetar is so immense that we on Earth can feel its ghostly touch across the void. In 2004, a magnetar located 50,000 light-years away, halfway across the Milky Way, unleashed a flare so powerful that it compressed our planet's magnetic field and ionized the upper atmosphere. For a brief moment, its distant fury from a star that died millennia ago physically reached out and touched our world. It serves as a stunning reminder that the universe's most violent forces are not abstract concepts, but distant, palpable powers that can reach across the galaxy. These magnetic monsters are not the only titans stalking the cosmos. Beyond the sheer weight of stars like R13601, there exists another class of Leviathan defined by a breathtaking physical scale. We call them hypergiants, and they represent the ultimate expression of stellar inflation. While a star like R13601 is mind-bogglingly massive, hypergiants are mind-bogglingly vast. Consider VY Canis Majoris or UY Scuti. These are not mere points of light, they are colossal orbs of tenuous gas with radii over 1,000 times that of our Sun. If you were to place UY Scuti at the center of our own solar system, its bloated outer atmosphere would reach beyond the orbit of Jupiter, completely engulfing the inner planets. The sheer volume of space these stars occupy is almost impossible to fathom. You could fit over 5 billion of our suns inside the shell of a single hypergiant. Yet here lies the fascinating paradox. For all their incredible size, these stars are often far less massive than the heavyweight champions we have discussed. A hypergiant like VY Canis Majoris likely contains only 20 or 30 times the mass of our Sun. How can something so large be relatively lightweight? The answer lies in its advanced age and profound instability. These stars are not in the prime of their lives. They are ancient, highly evolved monsters that have exhausted the hydrogen fuel in their cores. In response, their cores have contracted and heated up, causing their outer layers to swell to a truly monstrous degree. Imagine a handful of cotton candy. It is mostly air, a diffuse cloud of sugar that occupies a large volume but has very little actual substance. A hypergiant is the cosmic equivalent, a star that has puffed itself up into a vast, tenuous, and incredibly fragile bubble. This inflated state comes at a terrible cost. The star's grip on its own outer layers is incredibly weak. Its gravity, diluted across such an enormous volume, struggles to hold onto the star's own atmosphere. This makes hypergiants wildly unstable, prone to colossal eruptions where they violently expel huge amounts of material into space. They are not steady beacons, but rather flickering, unpredictable volcanoes of gas, shuddering through the final, chaotic chapters of their existence before their inevitable and spectacular demise. This volatility is perfected in a star like Rho Cassiopeiae, a yellow hypergiant caught in a cosmic identity crisis. It is a star of unimaginable scale, so luminous and vast that despite being located thousands of light-years away, it is just barely visible to the naked eye in our night sky. Yet its true nature is not one of serene stability, but of profound, shuddering instability. Yellow hypergiants occupy a precarious and fleeting phase in a massive star's life. They are caught between two states, having exhausted the hydrogen in their core and now burning helium, causing their outer layers to swell into a vast, turbulent, and incredibly tenuous sphere. These stars are not merely large, they are unstable to their very core, prone to violent pulsations that ripple through their entire structure. The delicate balance between the outward push of radiation and the inward pull of gravity is constantly teetering on a knife's edge. This results in titanic convulsions where the entire star expands and contracts rhythmically, like a cosmic heart beating in slow, violent throbs. During these intense pulsations, the star's grip on its own outer atmosphere becomes so weak that it cannot hold on. It does not gently shed material, it violently ejects it. In events that can last for just a few months or years, a yellow hypergiant can blow off a shell of gas with a mass equal to our entire sun. Imagine a single star in a fit of cosmic rage, expelling the equivalent of our entire solar system's central furnace out into the void. For Rho Cassiopeiae, this is not a hypothetical scenario. In the year 2000, astronomers witnessed exactly this. The star's surface temperature plummeted as it ejected a colossal cloud of material, which then cooled into a vast shroud of dust, temporarily dimming its light. This dramatic shedding of its outer skin is the star's desperate attempt to stabilize itself, to find a new equilibrium after the profound changes happening deep within its core. This violent process of self-stripping is the direct pathway to an even more extreme existence. By ejecting its hydrogen-rich outer layers, the star is relentlessly peeling itself down, moving inexorably toward its final, bare-bones form. It is evolving directly into a Wolf-Rayet star, that exposed, searingly hot core we discussed earlier. The journey of a yellow hypergiant is a spectacular public display of a star's private struggle, a visible, turbulent transition from one state of being to another, proving that the most massive stars often lead their most dramatic lives not in their birth or death, but in their chaotic, transformative middle age. Eta Carinii stands as a permanent monument to stellar instability. This is not a distant, theoretical giant, but a volatile neighbor right here in our own Milky Way, a star that has already given us a terrifying preview of its power. In the 1840s, it erupted in an event astronomers call the Great Eruption. For over a decade, it blazed with such ferocity that it became the second brightest star in the entire night sky, outshone only by Sirius. It was a cataclysm visible to the naked eye, a star apparently tearing itself apart in real time. When the cosmic dust settled, literally, the eruption had ejected at least 10 solar masses of material, forming the beautiful and bizarre homunculus nebula, a twin-lobed cloud of gas and dust that still expands around the star today. This was not a supernova, it was something else entirely, a colossal stellar outburst that left the star intact but forever changed. We now understand this event was likely driven by a violent cosmic dance. Eta Carinii is not one star but two. The system is dominated by a hypergiant primary star, a behemoth with a mass between 100 and 200 times that of our Sun. It is orbited by a smaller, yet still monstrous companion star weighing in at around 30 solar masses. These two titans swing around each other in a highly elliptical 5.5-year orbit. When they make their closest approach, their stellar winds, each a hurricane of particles streaming from their surfaces, slam into one another at millions of miles per hour. This collision creates a cacophony of X-rays and generates unimaginable turbulence. The prevailing theory suggests that the Great Eruption was triggered by one of these close encounters, where the gravitational and radiative forces from the smaller star violently disturbed the bloated, unstable outer layers of the primary hypergiant, causing it to shed an entire solar system's worth of mass in a single, protracted convulsion. This binary interaction makes Eta Carinii a ticking time bomb. The primary star is so massive and so evolved that it is teetering on the edge of collapse. It is one of the most promising candidates in our galaxy for a future core collapse supernova, an event that could happen at any moment in the cosmic sense within the next several 100,000 years. When it finally does go, its proximity, a mere 7,500 light-years away, will provide an unparalleled celestial spectacle. It will shine with the intensity of a full moon, visible even in broad daylight, a final, dazzling testament to the life and death of a true stellar monster. The sheer power of a supernova raises a chilling question. What would happen if one of these stellar cataclysms occurred in our own cosmic neighborhood? The answer depends entirely on distance. A supernova within about 25 to 50 light-years of Earth would be far more than a beautiful light show. It would be an existential threat. The primary danger would not be the initial flash of light, but the prolonged blast of high-energy radiation that follows. For months, the dying star would flood our solar system with intense gamma rays and X-rays. This radiation would not reach the ground, but it would have a devastating effect high above us. It would rip through our planet's protective ozone layer, chemically shredding it apart. With our main shield against the sun's own harmful ultraviolet radiation destroyed, the surface would be bathed in biologically damaging UV light for years. The consequences for the global ecosystem would be catastrophic, leading to widespread extinctions, particularly among plankton and other vital base organisms of the food chain. It is a scenario that scientists believe may have already occurred in Earth's deep past, contributing to previous mass extinction events. This terrifying possibility, however, comes with a crucial and comforting caveat. There are no known massive stars currently poised for a supernova within this lethal radius. The familiar red giant Betelgeuse, often cited as a candidate for a nearby explosion, is located safely over 500 light-years away. At that distance, its demise will be a spectacular celestial event, potentially visible in broad daylight for weeks, but it will pose no physical danger to life on our planet. Its light will be a brilliant memorial to a distant giant, a reminder of the universe's power that is awe-inspiring but mercifully not close enough to harm us. These cosmic cataclysms are the universe's ultimate element factories. Every massive star lives its life as a colossal nuclear forge, but its death is where the true cosmic alchemy happens. Deep within its layered core, over millions of years, it methodically fuses lighter elements into heavier ones. It begins with hydrogen fusing into helium, then helium into carbon, and so on, building a layered onion of elements all the way up to iron. But iron is a dead end, the atomic ash that chokes the star's central fire. It is the supernova explosion itself, in its unimaginable violence, that completes the process. In the heart of that cataclysm, amidst a blizzard of neutrons and unimaginable energy, a frantic process called rapid neutron capture occurs. Atomic nuclei are bombarded by a flood of neutrons so dense and fast that they cannot decay, forcing them to grow into elements heavier than iron. This is where the universe forges gold, silver, lead, and uranium. Every single element on the periodic table, from the carbon that is the basis of life to the silicon in computer chips, was created in one of two places, either in the steady burn of a star's life or in the spectacular fire of its death. The oxygen you are breathing right now was fused inside a star that died billions of years ago. The calcium that strengthens your bones, the iron that carries oxygen in your blood, all of these were forged in the hearts of these long-vanished giants and then scattered across the galaxy by their final explosive acts. We are not just living in a universe built by stars, we are literally made from their ashes. Every one of us is walking, talking stardust, a living testament to the violent and beautiful lives of the cosmos's most massive stars. This cosmic enrichment process is the unsung hero of our own existence. The violent death of a massive star does not merely forge heavy elements, it actively seeds future worlds with the very ingredients for life. When a supernova's immense shockwave plows through the interstellar medium, it acts as a cosmic snowplow, compressing vast, quiet clouds of gas and dust. This sudden, violent pressure can be the final push that overcomes a cloud's internal resistance, triggering its gravitational collapse and igniting the birth of an entire new generation of stars. But the supernova's gift is twofold. Entwined within that expanding shockwave are the freshly minted elements from the star's interior, a rich cocktail of oxygen, carbon, iron, silicon, and all the other complex atoms forged in its life and violent death. This polluted material mixes with the primordial hydrogen and helium of the collapsing cloud. When the new star forms at the cloud's center, the surrounding disk of leftover material, now infused with these heavy elements, begins to clump together. Without this stellar pollution, planets would be very different. The only worlds that could form would be gas giants, vast orbs of hydrogen and helium with no solid surface. It is the dust, the microscopic grains of silicon and carbon and iron from that long-ago explosion, that provides the seeds for rocky planet formation. These dust particles stick together, building pebbles, then rocks, then planetesimals, and eventually entire worlds. Our Earth is one such world, a collection of atomic ash from countless stellar explosions. The iron in our planet's core, the silicon in its rocky mantle, the oxygen in our water and air, all of it was delivered by the death throes of massive stars that lived and died long before our sun was even a glimmer in a nebula. Without these titanic stellar furnaces and their catastrophic finales, our solar system and the pale blue dot we call home might never have existed at all. Our new eyes on the cosmos are peeling back the veil of dust that has long hidden the universe's greatest dramas. The James Webb Space Telescope, with its revolutionary infrared vision, is fundamentally rewriting the story of massive stars. For decades, our view of stellar nurseries, the violent regions where these giants are born, was like trying to watch a play through a thick, dark curtain. Visible light telescopes could only see the outer edges of these cosmic clouds, but infrared light slips through the dust like a whisper, allowing Webb to see directly into the heart of the action. It is capturing the earliest moments of a massive star's life, watching as colossal knots of gas collapse under their own weight, igniting their nuclear furnaces for the very first time. We are no longer just theorizing about how these behemoths form. We are witnessing it happen in real time across the galaxy and even in our neighboring galaxies like the Large Magellanic Cloud. This is not just a clearer picture, it is a whole new dimension of understanding, revealing the intricate physics that govern the birth of a giant. Beyond our galactic neighborhood, Webb's power stretches back across time itself. It is detecting the telltale signatures of massive stars in galaxies so distant their light has been traveling to us for over 13 billion years. We are seeing the universe in its raw, chaotic youth, a time when the first generations of stars were lighting up the cosmic dark. By analyzing the specific chemical fingerprints in the light from these primordial galaxies, Webb is helping us determine the masses and life cycles of those first, elusive population 3 stars. Did they truly grow to 1,000 solar masses? How quickly did they live and die, seeding the pristine cosmos with the first heavy elements? The data streaming back from this engineering marvel is turning theoretical speculation into concrete knowledge, giving us a front-row seat to the very processes that built the modern universe. The universe's most brilliant finales are sometimes a lie. A star can stage a performance so spectacular we mistake it for its own death. A cosmic magic trick where the magician remains on stage after the grand explosion. These are the supernova imposters, colossal eruptions from unstable hypergiants that shine with the ferocity of a genuine supernova, yet the star survives the event. The Great Eruption of Eta Carinæ was the quintessential example, a 19th-century outburst that convinced astronomers they were witnessing a stellar death. only for the star to dim and reveal it was still there, forever changed but very much alive. These events are not true core collapse explosions, but rather titanic surface eruptions where the star violently ejects a huge portion of its own outer envelope into space. The physical mechanism is a desperate struggle against gravity itself. In these bloated, evolved giants, the outward pressure of radiation from the core becomes so immense that it overpowers the star's own gravity in its outer layers. The star does not explode from the inside out. It essentially blows its own atmosphere off in a sustained, violent gust, a stellar fever dream that can last for years or even decades. Distinguishing an imposter from a true supernova is a critical and often difficult task for astronomers. A real supernova typically shows a characteristic light curve, a sharp rise to peak brightness followed by a steady decline powered by the radioactive decay of elements forged in the blast. An imposter's light curve is often more erratic and prolonged, and its spectrum tells the true story. Instead of showing the high-velocity elements from a shattered core, it reveals the slower-moving, hydrogen-rich debris of a mere surface explosion. These events force us to question what we think we know about stellar stability. They reveal that the final chapters in a massive star's life are not a simple march toward collapse, but a chaotic, unpredictable series of fits and starts, where the star violently reorganizes itself multiple times before the final curtain falls. Every detected imposter is a challenge to our models, a reminder that the universe's most massive stars can defy our expectations until their very last second. These first stars are the ultimate cosmic ghosts, the missing link in our universe's history. For years, they were merely a theoretical dream, a class of stars known as Population 3. Born from the pristine hydrogen and helium that emerged from the Big Bang, they contained not a single atom of carbon, oxygen, or iron. Without these heavier elements to help them cool and fragment, the clouds that collapsed to form them could grow to staggering, almost mythical proportions. We believe these first stars were unlike anything in the modern cosmos, colossal titans with masses that could have ranged from 100 to well over 1,000 times that of our Sun. Their lives would have been a blaze of glory and violence. They would have burned at searing temperatures, pouring out immense amounts of ultraviolet light that began to tear apart the neutral hydrogen gas filling the early universe, a process called reionization. They illuminated the end of the cosmic dark ages, but their own light was tragically brief. Living for only a few million years, they died in spectacular supernovae that were likely far more energetic than anything we see today. These first explosions were the crucibles that forged the very first heavy elements, polluting the pristine cosmic gas with the ashes of carbon, oxygen, and silicon for the very first time. Every star that came after, including our Sun, carries the chemical fingerprint of that first violent generation. Yet for all their importance, we have never seen one directly. They lived and died in the universe's infancy, so far away that their light is incredibly faint and stretched into the infrared part of the spectrum by the expansion of the universe. Finding them has been one of astronomy's most elusive goals. Now, the James Webb Space Telescope is turning that dream into a tangible possibility. With its powerful infrared eyes, Webb is not just looking far across space, but deep back in time, to an era only a few 100 million years after the Big Bang. It is searching for the unique chemical signatures that will be left behind by the death of a Population 3 star. A supernova from a pure hydrogen and helium star would leave a very distinct imprint in the light of a distant galaxy, one devoid of the heavier elements we see in later explosions. Webb might also catch a glimpse of the stars themselves, not as individuals, but as clusters of brilliant, blue, and incredibly massive objects within the earliest galaxies. Finding even the ghost of one of these first giants would be a discovery for the ages, finally allowing us to witness the moment the universe switched on its lights and began its long, slow journey toward building everything we see today, including us. The next chapter in our understanding of these giants is already being written, not in the stars themselves, but in the ambitious blueprints for a new generation of telescopes. Our quest to unravel the mysteries of massive stars is accelerating, driven by colossal new eyes on the cosmos. On the ground, projects like the Extremely Large Telescope, or ELT, are rising from the desert floor. With a primary mirror stretching an incredible 39 meters across, this behemoth will collect more light than all of the largest historical optical telescopes combined. Its unprecedented resolution will allow it to see a football field on the surface of the moon, a level of detail that will let us peer into the very hearts of dense stellar nurseries. We will watch individual stars form in real time, resolving the complex dynamics of gas and dust that lead to the birth of a giant. In space, future missions will complement this ground-based power, observing the high-energy universe with instruments far more sensitive than anything we have today. These observatories will detect the faintest X-ray whispers from newborn black holes and the subtle gravitational ripples from distant supernova, giving us a multi-messenger view of stellar life and death. With these tools, we are poised to answer fundamental questions that have lingered for decades. Is there a true, unbreakable upper limit to a star's mass, or can exotic formation processes in the early universe create even larger monsters than R13601? We will witness the elusive pair instability supernova in action, not as a theoretical model, but as a real event, confirming the exact mechanism that vaporizes a star completely. We will conduct a vast cosmic census of massive stellar binaries, finally understanding just how common these tumultuous partnerships like Eta Carinae truly are, and how their chaotic dances dictate their final fates. The story of the universe's most massive stars is far from complete. Every new observation, every fresh datum from these incredible machines adds another sentence to their epic narrative, a narrative written in fire and light across the expanse of the cosmos. Their journey is one of impossible extremes, from their staggering birth in chaotic stellar nurseries to their spectacular and violent deaths. The universe's most massive stars are the ultimate expression of cosmic power. They live fast, shining with the light of millions, only to burn out in a cosmic instant. Their immense gravity forges elements deep within their layered hearts, and their final supernova explosions scatter those building blocks across the galaxy. These titans are not distant curiosities. They are fundamental engines of creation, the cosmic foundries that forged the iron in our blood, the oxygen in our air, and the calcium in our bones. Every one of us carries the legacy of these long-vanished giants. The next time you gaze up at the night sky, remember that you're looking at a universe built by stars. Let us know in the comments which of these 30 facts reshaped your understanding of the cosmos the most. Your sense of wonder is the truest tribute to these celestial behemoths.